Okay, good afternoon. And so the first talk in this session is by Howard, and he will talk about quantum state smoothing cannot be assumed classical.
Thank you, Abhishek. Does that sound good? Yep. Okay, so this is the last time you have to see me. You'll be thankful. So this is more of a research work. I'll be talking mainly about work published just in 2023. And so this is work with, first author on the paper is Kian Laverick, who was my PhD student. He's now, so anyone who hasn't seen my other talks, I'm at Griffith University here in Queensland, Australia. So he was my PhD student or postdoc at the time. He's now moved on to a postdoc in Singapore, in Maju Lab with Alexia or Fev. Prahlad Varshavsky, who is sort of a PhD student, sort of an independent researcher, contributed. Arya, who gave the last talk, who was a postdoc for me for a long time and is now at Mahadhan University in Thailand. And of course, that's me, right? So I'm going to begin. So I have this term quantum state smoothing in the title, and nobody else has talked about this at this workshop. So obviously I will explain what that is. But I'm going to begin by motivating by talking about prior work and ideas leading up to this idea of quantum state smoothing. And then I'll define it and summarize what the main results are in the paper. And then I'll show how we prove this with a very simple system and just go through the results and conclude. Okay, so the sort of motivation, I want to start by considering classical estimation. And so let's consider estimating a variable, a random variable x at some time tau. There are obviously there are many senses in which we could estimate it. We could give its mean, or we could give its median. Oh, whoops! I still haven't fixed that. Okay. There are different estimates we could give for this quantity, but all of the estimates I could give are wrapped up by my saying what the probability distribution is for that quantity. So this is my knowledge about this random variable x given by this wiggly p of xi here. So right, there are different. So this is what I'm going to take to be classical estimation. The problem of classical estimation fundamentally would be to determine this probability distribution, because that gives us everything else. Now, there are different ways that we could do this. One, so in terms of having a continuous measurement, so that's going to be the connection to quantum trajectories. And just say this is a diagram adapted from something by Mankade Tsang in 2009. We can consider the measurements which we have taken up to the time where we want to make that estimate. And then the type of estimate which you have in that case is called the filtered estimate, or its process is called filtering. So this state, well, okay, I'm going to call it a state because it's going to be analogous to the quantum state. This probability distribution is the filtered probability distribution or filtered state because I can obtain it by writing down some generalized sort of filter of the measurement records so far. There's also a thing called retrofiltering, or a process called retrofiltering, and there's a quantity associated with that, which is not directly the probability of xi given the future record. Sorry, I should have said retrofiltering, because that involves the future record, the record after the time that I'm interested in. But this function of xi, which I'm going to call E for reasons that will become apparent, is actually the probability of getting those future records given that the state was xi. And I'm also going to be making here a Markov assumption, or I mean, there might be a different term for that, but essentially it's like a Markov assumption, which is that if I knew what xi, the value of xi is, that would screen off the past measurement record. So in other words, if I knew that, that's sufficient to tell me the probability of the future records. So putting these two things together, if I now ask naturally, well, what if I just look at all the observations, both in the future and the past of the time that I'm interested in, what can I say about the probability now? Given these definitions and this condition, the probability, and just using Bayes' theorem or probability manipulation, the probability of xi given the record both times, and I guess hopefully everybody figured out that a left arrow means the past and a right arrow means the future, and a double arrow means both past and future. So this probability condition on both past and future is just proportional to the product of these two functions. And if I want to normalize it, I just normalize it. Okay, and so this probability is called the smooth probability, and this process is called smoothing. And there are reasons behind that which relate to sort of very simple examples. But yeah, I'm going to use in the same way of filtering, but yeah, I will use the term to mean in the completely general case. Okay, so that's the classical estimation. What's the quantum analog? So this is something which Klaus talked about in his first talk, I believe, and which he called the idea of past quantum states of a monitored system. So they're filtered. So this analogy I've already talked about, and maybe other people have already talked about. There's a very close analogy between the filtered state, the filtered probability distribution classically, and the filtered state in the quantum case, which is just the solution of the quantum trajectory equation. So just this is the state conditioned on the measurements up to the time that we're interested in. And there is also a very nice, simple analog of that quantity E, which I introduced before. It's actually a positive operator, which is a POVM element. I think Klaus said that he called it E because I called it E. And if you want to know why I called it E, it's because Chris Fuchs calls it E. So that's why it's E. I don't know why he calls it E. So this retrofiltered effect is, so it's a PRVM element in the sense that if I sum over all the possible future records of this thing, then I should get the identity matrix or identity operator. Right, and Klaus told you how to calculate this, I believe. Am I right? Using Krauss operators. Okay, so I'm going to assume that that was understood, and I guess if people want to know the details, they can ask me at the end if we have time. But I'm going to hope that you remember how these things are calculated. Okay, so that was some very nice work. So I should say, so Klaus defined the past quantum state as basically this pair of things. But actually, the idea of putting together a pair of things, one coming from the past and one coming from the future, is a much older idea in quantum mechanics. So there's the paper by Aharonov, Bergman, and Leibovitz in 1964, and then a more explicit formulation by Aharonov and Rohrlich, where they talked about a two-vector formulation of quantum mechanics, meaning one from the past and one from the future. And the relation, I would see this as just it's a special case of this general formalism here, where the future, this not F for future, F for filtered, where the state coming in the past, that you initially prepared some pure state, and then it underwent some unitary evolution from time t0 to time tau. And similarly, what they were considering was that at the final time, there was a rank 1 projective measurement that was performed, which corresponds to a final state phi, and that evolves backwards in time to the time tau, and that defines the ER. Okay, so hope that simple analogy helps make it clear. All right, so that's smoothing and, it's not smoothing. That's filtering and retrofiltering. What about smoothing? So classically, remember, we just multiplied those two things together to get the smooth state. So naively, you might say, well, in quantum mechanics, why don't we do the same thing? Just multiply these two operators together and normalize them. Well, the problem is, well, in general, this is not even Hermitian. We could symmetrize it to solve that, but even when we do that, we don't necessarily get something positive. Okay, so we can make it Hermitian, but it's just not in general positive. However, interestingly, this does have a meaning, this naive smooth state. It actually corresponds to, if I use this state to calculate expectation values, they turn out to be exactly the same as the weak value expectation values that, again, Aharonov coming up, Aharonov, Albert, and Weidman published about in 1988. So just in case you know about weak values, basically, if I do a weak measurement at that intermediate time tau and ask what's my expected value of that weak measurement, you can calculate that using this operator as if it were the state at that time. Okay, you can't in general do that for strong measurements. Klaus talked about the proper way to do it for strong measurements, but this does have a meaning. Okay, and yeah, in this paper they were only considering the pure state case. So that's really just an aside, okay, about you can do this, and it does have some meanings, but I obviously can't in general think of it as a state. It doesn't have the, it's not a positive definite operator, so yeah, it doesn't have the usual meaning. However, squared, right, now we get back on track. If these two operators commute, then I can multiply them together and get a positive Hermitian result. So that's just writing it out. Okay, so that means that they can be diagonalized in a common basis, and then that would mean that this naive state here would also be diagonal in this same basis. And in fact, this smooth probability distribution is exactly the product of this probability, this probability distribution and this probability distribution here. Okay, so in this case, everything reduces back to the classical case, as you might expect. And so this idea, right, that if these commute, then I can just essentially use classical smoothing, has been applied to quantum systems. So I think, as far as I know, the first example was in this paper from Abhishek's group in 2009. And so this was looking at switching between two different bistable states in cavity QED. And the red line here is a particular type of smoothing compared to the filtering, which is the jaggedy data. This is the paper that got me started thinking about this whole field, trying to understand what on earth are they actually doing if this is a quantum system and they're doing smoothing. Okay, but there are another couple of papers from Klaus and collaborators. I think Klaus, so this one is for atom quantum jumps, and this one I think Klaus talked about the photon number evolution in a cavity. And what's being plotted here. So this one is the clearest one to talk about what's being plotted. So as I think Klaus said before he corrected himself, that this is the probability distribution for the inferred number of photons in the cavity when you're continually monitoring that number by sending atoms through. But this is the smooth probability distribution, not the filtered one. Yes? No. So this is not generic at all. This is a very particular type of situation which simplifies the problem greatly. So this is, it's not generic for quantum systems at all. No, I don't believe so. No. I mean, I will be talking about Markovian systems where this does not apply. And I'm sure there are non-Markovian systems where this would apply. So no, I don't think there's anything, no. So this, basically, I don't have a picture of the filter, but you can get an idea of why it's called smoothing, is that you get plots which are just much smoother when you do smoothing compared to when you do filtering. Okay, so, all right, so that's not the end of the story, obviously, right? It seems like it works in this case, right? If I have, if my retrofiltered effect and my filtered state commute or have a joint basis, then, right, defining the smooth state in this way, right? So just basically doing classical smoothing at the level of the probabilities and then multiplying by this projector, that certainly defines a quantum state. It is a single state. It's not a pair of states. So it's a smooth state in exactly the same sense that classically I just have a probability distribution for my smooth state. It has the property that if I integrate over the possible future records of my smooth state, I just get back the filtered state. And so that's also a property that the classical one has, and that you would want to have that as a property of a smooth state. These conditions are set out in a paper that sort of appears at the end. And yeah, so I think I said that as well. It's a genuine state, it's positive and Hermitian. Okay, but the question is it the smooth quantum state? So it's certainly a smooth quantum state. We say that it is the smooth quantum state under the condition that this is my filtered state and this is my retro-filtered effect. And the message of my talk is no. Okay, it's a smooth state, but it's not necessarily the smooth state. And so the point is that there's a more general way to define a smooth quantum state that's not limited to these conditions. And satisfies these three conditions, and moreover is an optimal estimate of a true quantum state in the sense that I'll eventually get to. And with this more general definition, one sees that this particular solution only arises with an extra assumption, and that extra assumption is that the true quantum state is always one of these basis states, psi. But that's not guaranteed from the fact that these have this form. Okay, and that's the crucial point. Okay, so yeah, we're going to, okay, so here's a background to, so I guess that everything I talked about there could sort of be understood by people who knew nothing about continuous measurements. So this is a bit of background for people who haven't. I mean, I think this is the sort of things that everybody's been saying for the last 2 weeks. Yeah, master equation, continuous monitoring without changing the master equation on average, but monitoring the environment yields a filtered state, right, which on average gives the master equation evolution, can be jumps or diffusion. Yeah, there's the average, and you have different unravelings, right? I talked a lot about that last week, and that's going to be crucial to the story I'm telling today, that just because the master equation is fixed doesn't mean that the type of unraveling is fixed. Okay. So the idea of quantum state smoothing was introduced by my then PhD student Ibon Guevara, who was mentioned in Aria's talk before lunch, and the work that the map there that Aria talked about was developed for this purpose, but doesn't have any actual particular close relation to smoothing. So just to get that out of the way. All right, so this is the scenario that we were considering in this quantum state smoothing paper. And yeah, so it took quite a long time from my hearing about that 2009 experiment for this paper to appear, but that seems to be the typical timescale that papers get out in my group, which is not ideal. But anyway, we're going to consider two parties. Okay, do we have an Alice and a Bob? And Alice is the one who's doing the filtering estimate for a start. So Alice is making some observation, getting result O here. That's observed by her. And on the basis of that, she can estimate the state of this quantum system here, which, as I said, is the filtered state. There we go. Bob is also monitoring. So the point is this state has more than one bath. It's losing information in more than one direction. Bob is making his own measurement on the bath here. But we're going to say he also maybe has a telescope or whatever, and so he can spy into Alice's lab and see what Alice is measuring. So Bob has all the information. So we can think if everything was perfect then, that Bob would know he would know the state of the system as a pure state. And we know that in quantum mechanics, then there's nothing more to know. If you know the state of the system as a pure state, then we might as well think of that as the true state of the system, because that can't be refined. So we're going to define the true state of the system as the state that Bob knows by his all the information that he has. So Alice's task then is to estimate the state of the system, but we could also say her task is to estimate what Bob knows. Right? Because Bob knows as well as possible what the state of the system is. So instead of thinking of filtering as being directly to estimate the state here, we could also think of filtering as being, let Alice try to guess what Bob's state is. So this is the state, so U stands for unobserved by Alice, but obviously it is observed by Bob. So she could try to guess what Bob has seen and average over all the possible things that he might have seen, conditioned on what she actually saw. Okay, so that's another way of defining how she could do the estimate. And for filtering, right, if both of these are at the same time, it gives exactly the same as if she just completely ignored Bob. Right? It makes no difference whether you think of the task as being directly doing filtering like this or to estimate what Bob is seeing or has modeled. But if Alice takes her measurement record in the future as well as the past of the time that she's interested in, and asks what's my best estimate of Bob's state at time t, say, taking into account what I've seen up to time t and what I see after time t, then it does, I can't reduce this to anything simpler. This is what we define the smooth quantum state to be, and it does, so this does depend, for example, on how Bob is actually doing his measurement. We'll get to that. So this, in a sense that I'll define later, this, because you're using more information, or Alice is using more information to make this estimate, this will be a closer estimate to the true state than the filtered state is, which is what you'd expect. And just as classically, smoothing gives you better estimate than filtering, so if I define this problem, so it is in the quantum case as well. Okay, so yeah, I think what's here is everything which I just explained with that picture. So I don't think I need to go through it. Maybe just this equation again. So as I said, so Alice's filtered state can be thought of as being averaging over the possible observations that Bob got, this U, given what Alice got up to that same time, multiplying by this will be a pure state, or at least we're going to assume it's a pure state in all our simulations. Yeah, that just reduces the usual filtered expression. Okay. Yeah, so that's what I said. So it's independent of how Bob monitors, whereas Alice's smooth state, as we're defining it, so the only difference is that now she's conditioning here on the future record, is going to be a better estimate on average. Okay. And so one way that typically turns up is it will be more pure, because the purity of that estimate in general is equal to the fidelity of the that state with the true state. Okay, so a crucial difference is that this smooth state does depend on how Bob monitors in Bath. It depends on what sort of unraveling he does. Just another point to make, that if Alice was capturing, yeah, you only get a non-trivial difference between smoothing and filtering if your filtered state is mixed, right? If Alice is missing some information, because then she can get a better estimate by doing something beyond filtering. Okay, but that's also the same for classical smoothing. Okay, so then this is the main result that I'm talking about. So the title is exactly the same, I think, as in the title of the talk. So yeah, so if we have commuting retrofiltered effects and filtered states, then if the true state is one of these states in the diagonal basis, then the whole problem reduces to classical smoothing, right? But if this is not true, then it doesn't necessarily, okay? That's the first result, is that you don't necessarily get the classical smooth state. The second result is that you don't even necessarily get a state which is diagonal in the same basis. And that's trickier to prove, but I mean, you have to work harder to find an example to prove that, but yeah, I'll show you that it does. And then thirdly, if I have time, that it turns out that it's not even the case that the classical case, like you might think that, well, at least classical smoothing is the most straightforward. Surely it gives you the best estimate of the true state. Surely the best thing to do would be for the true state to actually be one of these states and just use classical smoothing, not some weird quantum thing. But no, it turns out that for much of the time, you get a better estimate of the true state if it's not actually diagonal in this basis. Yep, so we can show all of these things with just a qubit, and this very simple master equation for a qubit. So there's no coherences here at all. These are all incoherent transitions. So it's only a two-level system. So this virtual state is just in there because we want to think about being able to unravel absorptive processes. Okay, and as somebody said, yeah, that's sort of difficult to do. But if we make an absorption, in other words, I shouldn't say absorption, an excitation. If we make the excitation happen by having some laser excite to a virtual state, which then decays down to the excited level, then we can detect this photon being emitted out, and in the right regime, where we eliminate this level, that just looks like an excitation going up, but we know when it happens because we could, in principle, detect a click. So the ones going in this direction are going to Bob. So these two processes are going to Bob. There's also, I put in a decay process over here, which is going to Alice, but we're going to treat that as being very, very weak, okay, just for mathematical simplicity, so we can do it all basically, almost analytically. We're going to treat this as a very small parameter. This, for reasons I can say later, we make this epsilon relatively small compared to gamma, so there's a ratio of 20 there. So the steady state, if I just solve the master equation, there's the master equation. Yeah, it's just a mixture of the ground and excited state, okay, and mostly ground state. So let's just do filtering first. So then we can ignore this side, right? That's just happening. But what Alice sees is what goes into her detector here, and she's just, yeah, going to do exactly this, just count the photons. So Alice is this is going to be a very rare process for Alice. So this lets me just consider one detection for Alice in isolation from all the other. So, you know, Alice's next detection is going to be way over there, and her previous detection was way over there. I can just concentrate in on this time here, which I'll define as time 0 when it so happens that Alice got a detection. Yep, that's what I said. Okay, so what does her filter state look like? Well, up until that detection, it looks like the steady state, right? Because the last time she got any information was way back then, and this delta is a tiny perturbation on the master equation. So this is basically just in the steady state, and then when she gets to detection, it jumps to the ground state, and then exponentially recovers back to the steady state. So hopefully that everybody finds that fairly intuitive. That's filtering. Okay, what about smoothing? So there's the filtered, yeah, so if I want to write it in equations, there's the filtered result. So steady state before time 0, and this relaxing from the ground state for above time 0. Now, the retrofiltered effect, if you calculate that, if the way that Klaus told you how to do it, it looks like this. So it's also different depending on which side of t equals 0 I am. So it starts off proportional to the identity, that's the no knowledge effect, right? That's saying I don't know anything about the system out here, right? And it stays that way until we get to the jump, but then before the jump, right, it goes from the identity up to the excited state, because if Alice got a detection at this point, the atom must have been in the excited state immediately before, so the equation seems to say, must have been in the excited state immediately before it emitted. And so, yeah, on the other side, it starts in the excited state and exponentially relaxes to the identity again. Okay, so that's what that looks like. And if I just multiply these two things together, I get a smooth state, I'll call this naive smooth state, which looks like this. So after the jump is exactly the same as the filtered state. Before the jump, as you get near to the jump, because now this is conditioned on knowing that the jump is going to happen, the state gradually goes up to the excited state at that point and then jumps down to the ground state. So that's what the smooth quantum state looks like in this case. And we can derive that from the theory which I told you before. If I define the unobserved by Alice record that Bob is seeing by his just making these photodetective measurements on the outputs here, then the pure state is indeed just going to be either the excited state or the ground state. And if you just run through the argument, you get exactly the same smooth state as I showed you before. But as I said, the interesting thing about the smooth state is that it depends on how Bob gets the information about the system. And so now we're going to move on to our result 1, which is where Bob gets the information in a different way. So instead of just counting the photons, now he's going to do homodyne detection. So this is a strong local oscillator with some phase coming into, so BBS is balanced beam splitter. And so, yeah, this interferes with the light coming from the system here, goes into these detectors. I take the different signal You've seen this sort of stuff before. That constitutes a homodyne measurement. And he's going to do it on both of his signals, and he's going to use the same phase, in fact, on both. And that means that the evolution of the true state is governed by this diffusive equation. So I haven't worried about normalization terms here. But yeah, so it involves these Wiener processes. You've seen all this type of stuff before. So that's if I choose phi equals 0. So now I'll show you pictures later. But it's certainly not the case anymore, because this is diffusion, that the true state is either going to be the excited state or the ground state. It will, in fact, undergo a diffusion process on the Bloch sphere, but because of all the symmetries, it will just be on one great circle of the Bloch sphere. So I'm back to y equals 0 great circle. Okay, so Alice knows this. We're assuming that Alice, she doesn't know what Bob's results are, but we're assuming she does know what he's doing. She knows he's doing homodyne detection. So she knows that the state is somewhere on the y equals 0 great circle, but all she is seeing is clicks, right? And when she gets a click, she has no idea whether that would correspond to, like, whether x was, like, it gives her some idea that z must have been, like, above -1, right? And the higher z is, the more likely it is you get a click, but she has absolutely no knowledge about whether x is positive or x is negative. Okay, so the state still has the same diagonal form. It's still a mixture of the excited state and the ground state, but it's not the same as the smooth state we saw before. So in fact, so here is the solution. So you see it has some qualitatively similar things, that the excitation goes up as you approach a jump, but nowhere near as much, okay? It doesn't get anywhere near the excited state. So yes, you have a very different smooth state in this case, even though this is also an optimal estimate in a sense I'll explain. Okay, so that's result 1. You don't necessarily get the classical smooth state. Result 2 is to show that you don't even necessarily get the diagonal state. So here, right, so this is where it links into what I talked about last week. You might remember I talked about adaptive measurements, and particularly this idea of the paper from Karasik and myself, of making the system jump between particular states. So it turns out we can do a very complicated scheme here, where we make the atom jump between these 3 states, and it just cycles between them like this constantly. So the steady state is in there, but it's actually jumping between these 3 pure states. And that involves using a low reflectivity beam splitter, so you've got weak, so I'm only reflecting a tiny bit of this local oscillator, and yeah, but I get so I'm still have quantum jumps in this case, but they're very different types of jumps. And yeah, so this particular example was worked out by Prahlad Vashashki, and yeah, that's what we use. Okay, so yeah, so Bob is doing something very different, and in this case, just so remember, Alice really only has information about Z, but in this case, X and Z are correlated, you see. Like if I know that Z is up, Z is, likely to be higher, then that also means that this state is more likely to be the true state, because I've broken the symmetry of the problem completely with this ensemble. So, right, so in this case then the smooth state, defined in the same way, is not diagonal in the excited and the ground basis. And that's shown by this plot here. These 2 blue curves is showing the value of sigma x, and you see clearly it's not 0 as you approach this point where Alice has a jump. So that's just saying the same thing. We've proven that even though these commute, that doesn't mean that the smooth state is diagonal in the same basis in general. Okay, so here's a picture which explains what's going on. So this is at a long time before the jump. All of the states are close to the steady state in this case. So the green is the jumping, the regular excited ground state jumping. The blue is the weird 3-state jumping. The length of the stick is the probability that Alice calculates, the smooth probability that Alice is calculating. And this distribution here is it's the diffusive probability. So solving the Fokker-Planck equation on the ring gives us this equation here, or 2 Fokker, whatever. Anyway, we can solve it. But as you get close to a jump, you get very different sorts of behavior. So this probability goes enormously, but then so does this one in the other ensemble, and that's why the smooth state gets pulled way over here, whereas with the diffusive case, it just gets rid of the probability here and moves up the sides, and the smooth state sits down here. So completely different smooth states in the three cases that we've got here. All right, so I think I've just got time to mention something about cost functions. So, right, so we have a weird thing that so I talked about how the purity is equal to the fidelity, but you saw that the smooth state in this sort of classical case, the purity actually goes way down, and that's because the smooth state goes up from the ground to the excited through the middle of the block sphere. So you might say, well, but that looks like it's a worse estimate than the filtering, right? The filtering always stays pretty pure, whereas the smooth state gets very impure. So how can you say it's a better estimate? And the answer is that all of these estimates are defined with this cost function. So we call it the trace squared deviation, the expected trace squared deviation between the estimated state and the true state. And basically you have to define things like this if you want to get back the standard filtered state. So this is this is one of the cost functions which you can use to do that. You can't just arbitrarily pick a cost function and expect it to give you what corresponds to the normal filtered stage, for example. So in this case, right, okay, so if I actually look at this cost function, it is actually better for the smoothing does better than the filtering, which is what you'd expect. Okay, and then the final plot to show the final result is that now if I look at that cost function, which is also the Hilbert-Schmidt distance squared, if you prefer that way of thinking about it. So I look at the mean of that for the three different type of unravelings that Bob does, so the three different type of smooth state that Alice calculates, you see that it's actually, most of the time, it's lower for the homodyne or the weird adaptive one, is lower than what you get for the classical smoothing. So it's not even the case that you get the best estimate by using by having a classical type of scheme for Bob and for the smoothing. Okay, and yeah, so the conclusion is just summarizing everything I've said. And there's a bunch of other papers on smoothing in case you're interested, and also papers coming out or being prepared. But yeah, that's just for information, and yeah, maybe I'll put that back there to end. Thank you.
Hi, thanks for the talk. Can you go back to slide 20? 20. Oh, sorry, 21 then. Yes. So, Alice does not have complete efficiency, right?
Oh, well, Alice has complete efficiency on her channel, but her channel is a very small proportion of the total.
Yeah, but what I'm thinking is why the smooth state goes completely up to the excited, completely up to 1. I would think that, okay, definitely it will weight more towards the excited state just before the jump is coming, but why it completely up to 1?
Whoops, sorry. Because, so it doesn't, all right, so for this actual scheme, it doesn't. But if you're talking about the green curve.
Yeah.
Yeah, okay, so the green curve, okay, so this is where the green curve first comes up. Essentially because we're assuming, Alice is assuming that Bob is doing a perfect measurement. Okay, so therefore Bob always knows whether the atom is in the ground state or the excited state. So those are the only two possible options. And Alice knows they're the only two possible options. So if she sees a click, it must have been in the excited state. So even if she has low efficiency, yeah, if she sees a click, yeah, she knows it must have been excited. Does that make sense?
Yeah, but she is still estimating the smooth state by taking an average of over Bob's outcomes, right?
Yes. But yeah, so I don't know. Yeah, I'm not sure whether there's other circumstances where it would look different, but particularly in this case, because it's so simple in this case, it really does go all the way to the excited state.
Thank you.
Thanks for the nice talk. So I have a question. So about do you think that smoothing or filtering is better in finite time also, or just
like in discrete time? You mean?
I mean, is it asymptotic? I don't know, I'm not aware if there is any proof for that. For example, smoothing can give always better.
No, so I would not say that it always gives a better estimate.
Always?
But so I'm sure there is something one could say. I'm not sure precisely what it would be. But just with the general principle, if one is estimating on more information, then there must be some way to define it such that we can say that on average, one has a better estimate. Yeah, but it definitely won't be the case that in every particular run that it would be better. Yeah, you could just be unlucky.
And I don't know if there is any other work regarding to no Markovian, for example.
Not that I've thought about. No. There's definitely. I mean, yeah. So I guess I should say that So I do have a former postdoc who's finishing a project on estimating unknown parameters using smoothing rather than filtering, for example. And so you could think of that, if they're changing parameters, then that's an example of non-Markovian evolution. You could think of it that way. So one can certainly consider smoothing. Yeah, maybe I should have said, so Mankei Tsang's 2009 paper, he was introducing quantum smoothing in the sense that there's a quantum system, but for the purpose of just estimating classical parameters. So that allows for non-Markovian evolution in a fairly simple classical sense. Yeah.
Okay. Thanks very much.
Thanks for the talk. So if I imagine there was another copy of the epsilon channel for Alice.
Sorry, this one?
Yeah, exactly.
Right, so there was something
kappa
here.
Or whatever. How does the smoothing compare to the true state if you then change the representation? So you'd maybe mix the delta and this new channel so that they're no longer rank 1, so that you don't have certainty of the state after Alice detects a jump.
Yeah, then I guess it will become more complicated. So in general, it's not in general, you can't do this analytically or like numerically exactly as we've done here. In general, it involves essentially doing running heaps and heaps of possible records that Bob could have got, and actually working this probability out that's a non-trivial thing to do, which involves using linear trajectories rather than the nonlinear normalized trajectories. And so I haven't talked at all in general about how we calculate that thing, but yeah, in general, it's a complicated thing and it's hard to predict. Yeah, we've got some papers which are trying to get some intuitions about when does it work well, when is Alice well able to guess or estimate what Bob is seeing, and when is she poorly able to? And yeah, the results were not even according to our intuition. So I think there's an awful lot of richness in these sorts of questions. Yeah.
And is there any intuition as to how the filtering state does with time, as to whether it continues to get in the case that I spoke about, whether it continues to get worse or whether it sort of settles?
So sorry, I'm not sure.
So if you don't have the rank 1 jump, so that this is more obviously you can't compute this analytically, but just wondered if you have an intuition for how the good the smoothing state is as you progress in time.
I don't think there's anything general I can say. I suppose just to say that maybe just to point out some some of the simulations we did, we've done where are they? I left out, that's silly. Oh, no, okay, yeah, so this one, so this one and this one go together. So for example, we looked at continuous variable systems and homodyne type measurements. So very far from then all your measurements are diffusive, and so nothing is nothing is, you don't get a click which puts you in a rank 1 state or anything like that. So that's the typical situation where the state is never never pure at any time. But the nice thing about these is that you do have steady states. So we can compare the filtered steady state to the smooth steady state and say things about them. Yeah, how different are they? Understanding why, what makes one smaller than the other, that sort of thing. So there are, if you're sort of interested in general questions like that, you might get some intuition from there.
Great, thanks.
Yeah. Thank you.